In any empirical exercise, after the estimation is being done, it is very necessary to analyze the inference and also to draw some conclusions. And for this, the overall significance of any regression model is very much important. So this gets into the most important Gauss-Markov theorem. So by the Gauss-Markov theorem, we have already done the importance of the minimum variance property, which means that any estimator in any regression model will call for minimum variance unbiased property or the blue property. This has been discussed elaborately in the previous modules, and we have seen that an OLS estimator satisfies all the property of unbiasedness, minimum variance, consistent, and thereby efficient. So in this regard, it is very important to justify the importance of the overall significance of the model. And this gets down to the most important component to measure the goodness of fit, which is referred to as ANOVA, or analysis of variance. By ANOVA, we basically mean that what can be the sources of variation in the dependent variable. So in any estimation model, we get a functional relationship between the dependent and the independent variables, and also there is a relevance of an error term. So when we want to explain the explained variation of the dependent variable due to the independent variables only, we have a systematic component, and then we go for the random component. So when we discuss about the random component, this calls for the reference of the error term. And that is what the ANOVA is all about. So ANOVA basically deals with the systematic component and the random component. And also we want to analyze what are the sources of variation in this dependent variable. This calls down to the most important assumptions which are necessary to conduct the ANOVA. So one of the assumptions is that the distribution of the residuals must follow normality. And this assumption we are continuing from the very basic days of OLS regression. And secondly, when we want to explain the homogeneity of the variances, we want to say variances are equal across all the samples taken out of the population. So these two assumptions are very important to conduct the ANOVA. This boils down to an example of the ANOVA that we can discuss. For example, we want to take up a group of patients who are suffering from malaria, and they are given 3 categories of diagnosis. So on the basis of this category, we can explain which category of diagnosis will be more effective in curing this disease, and thereby we can get through an ANOVA table. So as we can see, an ANOVA table is to be constructed where the sources of variation can come up. This boils down to some of the important terminologies which shall be used in the context of analysis of variance. Firstly, we have means, which means a mean from the population or the mean from the sample. So when we consider about the grand mean, it is basically given out from all the range of values the mean is being conducted. And this is what we refer as the grand mean. And sample mean as if we are taking the observations from x1 to xn and we divide all the observations by n, thereby we get the sample mean. So the first terminology refers to the grand mean and the sample mean, as we can see. Second terminology is very important for understanding the overall significance of the model, and this calls for F statistic. F stands for Fisher statistic. So it is actually denoting the difference in the variances across the various samples of the population. So whenever we go for the F statistic, we want to find out what is the proportion which is explained by the variables which are dependent out of the proportion which is explained by the error term. So basically it's a ratio of measure of effect divided by the measure of error. So by error we mean the random component, and by effect we mean the dependent variables and the variation that can come up. Now we move on to the second important measure, which is about F, what are the values it can take. It is very clear from the ratio that F is the measure of actually variable or the effect divided by the measure of error. So if it is greater than 1, then definitely the measure of effect is greater than the measure of error. As a result, the explained variation will be more, and that will speak good about the model. Otherwise, if f is less than 1, then the measure of error will offset the measure of effect, and that will reduce the significance of the model. Next, we move on to the sum of squares. These are very important terminologies in the context of ANOVA. When we look at the sum of squares, it's basically a technique which explains what is the explained variation of the dependent variable. As we can see that it is basically taking the difference from the grand mean, and the difference of each observation from the grand mean can be either positive or it can be negative. So to avoid the negative values, we square it up. So sum of squares is basically given by summation of xi minus x bar whole square, which is one of the very important component of this ANOVA. Then we have the degrees of freedom, because as it is said in the estimation model already, and also we repeat it here, the degrees of freedom is number of observations minus the number of variables to be estimated. And it is a very crucial indicator to understand the overall significance. In this particular slide, we are going to take up the very important derivation of how total sum of squares can be decomposed into explained sum of squares and residual sum of squares. So here we find that yi is considered to be the observed variable of y, which is equal to yi hat, which is the predicted value, plus the error, which is the estimated value of the error ui hat, which is in the step 1. Now in the step 2, we are taking the difference from the mean, which is considered as the grand mean, denoted by y star. So after taking the difference, we are getting y1 minus y star equals to y1 hat minus y star plus u1 hat. On doing this, we are getting into small letters, which is yi equals to yi hat plus ui hat, and that is the step 3. So this is the deviation of each observation from its respective mean. Now we know that it can be negative or positive, and so we take it for all the observations, that is by summation, and we square it on both the sides. And after doing everything, we are getting step number 4, where in step number 4 we get summation of yi square, which is about the exact observation, equals to summation of yi hat square, which is on the predicted value, plus summation ui hat square, and this happens to be step number 4. Now we know from our regression model that yi hat is basically explained by the slope coefficient, which is beta hat, multiplied by summation of small xi. Here all the small letters indicate the deviation from the mean. So once we get that and substituting in step number 4, we are getting the step as it is, summation yi square equals to yi hat square plus summation ui hat square, which is step number 5. And by substituting this, we are getting the famous expression of summation yi square equals to beta hat summation xi square plus summation ui square. So in step number 6, we can explain that the total variation in yi can have two components, systematic and random. The systematic component is captured by ESS, which stands for explained sum of squares, and the random component is given by summation ui square, which is the residual sum of squares. This boils down to show different type of expressions for ESS, because that will be required after all to understand the goodness of fit. So we observe that here ESS is basically the difference between total variation minus the variation due to error. So this goes by the step 1, where we find summation yi square minus summation of ui hat square. On the basis of that, we know that this is equal to yi hat, because this is basically the ESS expression. Now we know from the step 3 that this can be written in terms of the slope coefficient multiplied by summation xi squared, which is the step 3. Now what we are doing here, we are basically substituting the expression of beta hat, which is written by summation of small xi yi by summation xi squared. Now if we square it up, then the entire expression gets squared up. And on the basis of the step 5, we find out the cancellation of xi square on both the sides. And we get down to the step 6, and thereby after simplification we get the final expression of beta hat summation of xi. So that means explain sum of squares can be written as beta hat summation of xi yi, or it can also be written as beta hat summation of xi square. So explain sum of squares plays an important role in explaining the variation of the dependent variable. On the basis of this, we arrived at the very important coefficient of determination, which is called R square and which measures the goodness of fit. So for any particular equation, the goodness of fit plays a very important role. So we observe that according to the expression of the correlation coefficient, which is by the Pearson, it's basically covariance divided by the variance. So we take R, which is covariance of xi yi, divided by root over variance of xi into root over variance of yi, and that happens to be the step 1. In order to get to the next step or step 2, we are squaring both the sides. So after squaring both the sides, we get in the numerator summation xi yi whole square, and since we are taking up the square root gets eliminated and we get the expression of the variance xi square yi square. Now we get into the step 3. In the step 3, what we are doing basically, we are decomposing summation of xi yi whole square and we are mentioning it elaborately. That is summation xi yi into summation xi yi divided by summation of xi square summation of yi square. And that is how the step 3 comes up. Now by the cancellation in the denominator, we are getting an expression of summation of xi yi by summation of xi square. This is one of the components of step 4, which is none other than beta hat, that is the estimated value of the beta, and the other component remains as it is. So after doing all this, we get beta hat, which is summation of xi yi by summation of yi square. So this is what we get in step number 5 after the simplification that is being done. Now we continue this proof because from the previous slide we repeat the step number 5 in this slide once more so that we can get the clarity of the matter. So we repeat the step 5, which is taken from the previous slide, where we write down the expression of R square once again, which is given by beta hat summation of xi yi divided by summation of yi square. Now what we know? We know that explain sum of squares can be the numerator, which is already derived, and total sum of squares is summation of yi square. So these two expressions are known to us. So hence we can write R square equals to summation of xi yi by summation of yi square, which is basically the repetition of step number 5. And now we can put down the respective expressions of ESS divided by the TSS. So R square basically can be greater than 1. R square can be basically less than 1, and on the basis of that we can see what is the variation of total sum of squares in the explain sum of squares. If we say R square equal to 1, then the exact variation is observed. If we say it is less than 1, then the variation is less or the unexplained proportion moves more. This boils down to show about the different expression of R square. Just we have shown different expression of explain sum of squares, that is ESS. In the same way, we can show in this slide different expression of R square. So as we can understand that total sum of squares is basically the summation of ESS plus RSS. Already this is the step 1. On the basis of that, we can figure out only the fraction of explain sum of squares. Now we divide by TSS in the entire equation. So after dividing, we are getting an expression which is ESS by TSS, which is none other than coefficient of determination, because TSS by TSS is 1, and we have the ratio of residual sum of squares, which is RSS, divided by TSS. This happens to be step 3. When we move on to the step 4, we are just writing R square, which has already been shown, which is equal to 1 minus RSS by TSS as usual. So on the basis of the expression of RSS, we can put that it is summation of uy square, and on the basis of the expression of TSS, we can put it is the expression of summation of yi square. So hence we can prove the result that R square can also have this type of expression. So now we are ready to come to our most important statistic, which we have mentioned in the terminology, which is F, or the Fisher statistic. because on the basis of the Fisher statistic, we can explain the goodness of fit. So what is that? Under ANOVA, we know that the residual sum of squares follows n minus 2 degrees of freedom because there are two unknown parameters, alpha and beta, to be estimated. N is the number of observations. And ESS follows a chi-square distribution, which the degrees of freedom 1. Why 1? Because there are two parameters and there is one variable which is estimated, which is x. So 2 minus 1 happens to be 1. On the basis of that, we start with our F ratio, which is basically the sum of squares divided by the respective degrees of freedom. So we get explained sum of squares as mentioned in the step 1 divided by sigma square, which is the population variance, divided by 1, which is the respective degrees of freedom. Again, we have divided by the RSS, which is residual sum of squares, divided by sigma square again, and then we have n minus 2. This n minus 2 is the degrees of freedom. After simplification, we get step 2. So in step 2, we observe ESS by 1 divided by RSS by n minus 2. That is what step 2. So the expression of explained sum of squares is equal to this, and RSS is equal to summation of uy square. So we substitute in the respective places and we get step 3. So then we can easily prove that F is basically the ratio of residual sum of squares divided by the explained sum of squares, as it is shown in this particular slide. Now, as we move on to show how can we go for the relationship between this F statistic, which is measuring the overall goodness of fit, and R square, which is the coefficient of determination. So in order to do this, we have to again start from the total sum of squares, which comes out to be in the step 1. So we can observe TSS equals to ESS plus RSS, which is in the step 1. Now we write down the expressions of TSS and ESS separately, which is nothing but summation of yi square as mentioned in the step 2, and ESS, which is equal to beta hat summation of xi yi, which is the step 3. Because these expressions are denoting the explained variation and total sum of squares is explaining the total variation. On the basis of this, we get the step 4. So in the step 4, what are we doing? We are dividing this numerator by summation yi square. At the same time, we are also multiplying this entire ratio with summation of yi square. So on the basis of that, we get the expression of r square, summation of yi square multiplied. This expression comes out to be step 6, which will be required in the forthcoming derivations. So as we can see in this slide, that we repeat step number 5 once more because it's a continuation from the previous slide. So in step number 5, we write it once again about the expression of ESS. Now from the expression of residual sum of squares, we know that it is the difference between total sum of squares and explained sum of squares. So we put the respective expressions. So under TSS, we have written summation of yi square. Under ESS, we have written r square summation of yi square. Now we can take summation of yi square common in step number 8, and we can write 1 minus r square in the bracket, because this step number 8 is basically the relation of RSS by summation of yi square. So now by the original expression of F, which is written in the step number 9, or by the definition of F, it is the ratio of explained sum of squares divided by the residual sum of squares. We put all the expressions here, and after putting all the expressions, we are getting step number 10, and by rearranging the terms, we can get F equals to n minus 2 r square by 1 minus r square. So that means in this particular expression, we can see that F and r square can be related. Basically, F and r square can have a relationship in this manner. So this is basically one of the steps which shows how the goodness of fit and the coefficient of determination can be done. get into the most important relationship in regard to the ANOVA, that is the relationship between f and t square. As we all know that f is basically the goodness of fit, which is measuring the overall significance of the model, and t square basically follows from a t distribution which measures the significance of the individual variables in the model. So this is basically linking up the overall significance with the individual significance. As we go by the derivation, we start with basically the expression of f. So expression of f is given by explain sum of squares divided by the respective degrees of freedom, which is 1, divided by RSS, that is residual sum of squares, divided by n minus 2. N stands for the number of observations, and minus 2 number of unknown parameters alphas and betas to be estimated in this two-variable regression model. Now we go for this expression, which is the explain sum of squares. So by definition, we know when we have written in summation of small yi, now we write down in terms of the capital letters as yi, that is the specific observation of y, minus y star, which is the grand mean, which is divided by summation of uy hat square, which is basically the estimated error of the residuals, divided by n minus 2. This n minus 2 happens to be the degrees of freedom. On the basis of this, we are basically writing in terms of a two-variable regression model where the estimated parameters are alpha hat and beta hat xi, minus we are taking its difference from their respective means, which means alpha hat plus beta hat x star, and we square it up, and we do it divided by sigma hat square, because this is basically being estimated or it is basically being observed. Now we actually go for the expression of beta hat square, because this expression after simplification, alpha hat gets cancelled, beta hat can be taken common, but if we remove the bracket it becomes beta hat square, and within the bracket we can write xi minus x star whole square divided by sigma hat square as usual, which happens to be step number 3. When we go to step number 4, we are basically writing summation of xi square, because we are converting the deviation from the grand mean into the small letter. So instead of writing summation of xi minus x star whole square, we are mentioning it in terms of summation of xi square. So this expression is none other than beta hat square by standard error of beta hat, which is the normal expression of t distribution. Since it is in the square form, we mention f equals to t square, which is the last step of this derivation. Now, in order to get the final expression of t square and r square, we go from the slide number 17, where we go for the step 1, which is the relation between f and r square. And from the slide number 18, that is the previous slide, we get f equals to t square. So these two derivations are done in the respective slides. Slide number 17 corresponds to this, and slide number 18 corresponds to step 2. Since both of them are equal to f, we can equate the expressions and we get the final expression of r square with the t square. Because if we go for r square equals to 1, then definitely we can see that t and f are equal, and that makes the most important proof with regard to the goodness of fit. Now we come to the summing up of these particular discussions on the goodness of fit. So first of all, in this module, we have discussed on the most important measure, which is the coefficient of determination, r square, which measures the explained variation out of the total variation. Then we have highlighted on the issue of F statistic, which measures the goodness of fit. And finally, we have also taken up the derivation, which is the outline of this entire module relating to TSS equals to ESS plus RSS. And accordingly, other derivations are done. So this will boil down to different kind of hypothesis testing, which will come up in the forthcoming modules.